Okay, so let's talk about algorithmic complexity classes. So let's start off and say this square here represents the space for all the problems that exist. Okay? This is all problems ever. Okay? So this P right here is the problems that we discussed in the second portion of the course, the problems we just discussed. So this is dynamic programming. This is shortest path for algorithms. This is strongly connected components. This is all the problems that that we looked at for that we could solve in polynomial time. Okay, that was all the problems that had efficient solutions. Right? Because when we talk about polynomial, we say polynomial means efficient. Okay? Now, in the first part of the course, we also talked about Turing machines, right? And Turing machines define the problems that are computable versus the problems that are not computable. Okay? So we break the space of all problems in two, and we say we have a set of problems that are computable. That includes the P problems we talked about in the second part of the course. And we have a bunch of problems that are not computable, that are undecidable, as we say. And we talk about that in the last part of the course. But P is definitely in the problems that are decidable, that are computable, right? Okay, so we have P. We have this. These are the problem space. These are the complexity classes we've discussed so far. Okay, so the question is, what other algorithmic complexity classes are there? So we have problems that require exponential space. This is probably one of the larger. This is one of the largest algorithmic complexity classes people talk about in standard algorithms course, and this includes lots of problems like looking at if regular expressions represent the same language. You're going to need an exponential amount of space. This represents. Oh, I should start by saying this represents all the problems that are solvable by a Turing machine in some exponential amount of space. Um, and yeah, and this is a lot of space. Then we have exponential time problems. Okay, the problems that need exponential amount of time. So this includes problems like succinct circuits. And then we have polynomial space problems. These are the problems that only require a polynomial amount of space to solve. Okay, so a good problem of that you might have seen before is if given a regular expression, seeing if the regular expression denotes all possible strings, if it's universal. There are other problems like various puzzle problems, but this is known as polynomial. These are simply all the problems solvable by a Turing machine that use a polynomial amount of space. Okay, so these are very large complexity classes and encompass most problems you'll ever have to deal with. Okay, so you don't really go up to these complexity classes very often. Many computer scientists don't. In undergrads, as part of their algorithmic studies, I don't see very many algorithms courses look at problems that are in exponential time, exponential space, even P space. Okay, but what we do look at are problems that are NP or co-NP. Okay, so NP stands for non-deterministic polynomial. The non-deterministic polynomial time, and NP simply means is the set of all decision problems solvable by a non-deterministic Turing machine in a polynomial amount of time. Okay, so this certainly includes the complexity class P, because this P complexity class is simply the amount, all the problems that are solvable by a deterministic Turing machine in polynomial amount of time. So a non-deterministic Turing machine would have a easy time solving any P problems. But also there are a bunch of problems that a non-deterministic polynomial machine could solve very rapidly. Okay, so think the SAT problem that we just discussed. A non-deterministic Turing machine. Remember, a non-deterministic Turing machine is simply one that evaluates multiple different possibilities at once. So a non-deterministic Turing machine with SAT would simply look at all the possible truth assignments for all the Boolean variables at once and simply return the truth assignment that evaluates the true, if there is one. Okay, so alternative, so all the problems here are all solvable by a non-deterministic Turing machine. Okay, an alternate definition for this, which we'll discuss in a moment, is that non-NP contains the problems whose yes instances are checkable in a polynomial amount of time by a Turing machine, a deterministic Turing machine. Okay, so there is a difference between NP. So there is a difference between problems that are checkable, whose yes instances are checkable. Let's think back to SAT. It's very easy if there's a yes instance, if it gives you a truth assignment, if there's a yes instance, if it gives you a truth assignment, it says, yes, here's the truth assignment that evaluates the true, that's very checkable, right? You just have to plug that truth assignment into the equation and deterministically check if it says a yes or no. What if the Turing machine gives you back, or the non-deterministic Turing machine gives you back a no? Okay? If you get back a no, then it means that there isn't a polynomial time, there isn't an assignment that satisfies that. But then how do you check that? How do you check that there is no possible assignment that satisfies SAT? You have to go through all the truth assignments, all possible truth assignments for the Boolean variables, and check and make sure none of the equation never evaluates the true for any of those assignments. That's a tall order. So we differentiate NP from co-NP because there are a set of problems whose yes instances are checkable in polynomial time, and there's a set of problems whose yes instances are not checkable in polynomial time. And so that would be, for instance, the tautology problem. So the tautology problem simply states that given a formula, does every single assignment evaluate to true? So if you get a yes in that case, then you have to still look at every single assignment and make sure it's not really, the yes instance isn't really checkable. But for instance, if you get a no instance, that if the tautology problem gives you that and say no, this assignment does evaluate to no sometimes, then you could check that assignment, check one possible no instance of the assignment. Okay, so these two together are based on the same idea, i.e. problems that are solvable by a non-deterministic Turing machine. But we separate them out because for some problems the yes instances is checkable in polynomial time, and for some problems the no instance is checkable in polynomial time. Okay, and for some problems both the yes and no instances are checkable in polynomial by a deterministic Turing machine in polynomial time. The big problem for that is integer factorization. Okay, so integer factorization simply says, given a number, is there a truth assignment? Given a number, is there a factor less than k? Given a number, does it have a factor that's less than k? Okay, remember this is a decision problem, so we have to include that. Is there something that's less than k? We have to have that extra input to simply make the output a yes or no. Okay, so with the integer factorization, the yes, there is a factor given there is a factor for this number n, is checkable because it could just give you the factor and you could calculate out what is n divided by this factor. For the no case, that there is no factor, there is no factor of n that's less than k. You could still check this in polynomial time by simply listing out the primes and listing out the primes and checking that they're primes using the AKS primality test. Okay, so integer factorization is in both, but most notably, integer factorization is not what's known as NP hard. Okay, so NP hard is not actually like these other complexity classes. Okay, this NP hard, this dash hard simply means that the problems that are in this area are as hard as the hardest NP problems. Okay, because so it doesn't mean that they're part of NP. Okay, that doesn't mean NP hard problems could be in P space, EXP time, EXP space. They could be undecidable even. Okay, NP hard does not necessarily mean a problem belongs to a certain algorithmic complexity. NP hard simply means that there are some problems that are so hard, they're harder than the hardest NP problems. Okay, so that includes some NP problems. Okay, but it includes a lot of non-NP problems. Okay, so NP hard. So these problems, the problems that are in NP, and the problems that are in NP, and the problems that are in NP hard, those represent the problems that are NP complete. Okay, so NP complete means a problem is both in NP, i.e. a non-deterministic Turing machine can solve that problem in polynomial time, and also that it's NP hard, that it is harder than all the other hard NP problems that exist. Okay, so this space here, NP complete, the reason it's important is because these are the hardest NP problems that exist. Okay, so all NP problems, all the problems in NP should be reducible to these two NP complete problems. Okay, because for any problem x in NP and y in NP hard, we say that x is reducible to NP hard, to y. Okay, and the reason why 3-SAT or SAT is important is because it is one of the OG NP complete problems. Okay, it's been proven to be a NP complete problem, and we're going to go through that next.